Okay, so now I'm start recording. Okay, recording. All right. So today we will talk about electromagnetic induction. Okay. So actually I lectured before, yeah, about this magnetic flux. Okay, if you still remember, and then I also talk a little bit about this Faraday's law, yeah, Faraday's experiment. So today we will look into details. Yeah, look into details, especially the equations. How we're going to use the equations and solve some problems. Yeah, solve some problems. So that day I just describe. Yeah, qualitatively. Today I will explain quantitatively. Yeah. Okay. So everybody can see the screen, right? Can see my screen, huh? Just to make sure everything. So 50 people around. Yeah, where are the rest 10 people? Okay. So electromagnetic induction, yeah, it actually generate in short I can say chapter 5 is about how to generate electricity. Okay. This one actually you should admit through MOE email, then you don't need to let me admit. You should actually admit using MOE email. Okay, so so chapter 5 is about how to generate electricity. Yeah, using using a coil and a magnet, right? Using a coil and a magnet. So generate electricity. So first, we must know about magnetic flux. What is actually magnetic flux? Okay, we already know magnetic flux is a measure of number of magnetic field lines through a cross-sectional area. That means, let's say this is a region of magnetic field. A region of magnetic field. So you have magnetic field lines in the magnetic field. So let's say we have a certain area in that region also, in the region of magnetic field. The magnetic field lines that passes through that area is called magnetic flux. So these, you can see these magnetic field lines all pass through this area. So all these magnetic field lines are called magnetic flux. Understand? So this area can have different angle theta, yeah, different angle theta. So what is angle theta from which direction to which direction? I will explain. Okay. So magnetic flux is defined as the scalar product between the magnetic flux density and the vector of surface area. So it's a product. Product means multiply. Multiply the magnetic field, yeah, magnetic flux density. Actually, magnetic flux density. Let me just you know just okay. Just copy this whole thing and put it over here. Yeah. Okay, so this uh, ma- um, magnetic flux density, this symbol is called we know is magnetic field strength, isn't it? Magnetic field strength. So it has another name we call magnetic flux density. Magnetic flux density. So magnetic flux density and magnetic field strength is the same. Okay, sometimes we call magnetic flux density, or sometimes we call magnetic flux, magnetic field, magnetic flux intensity. Yeah, sometimes we call density, sometimes we call intensity, magnetic flux intensity. So this magnetic field strength has another name called magnetic flux density. Okay, and also why we call it magnetic flux density basically is if we use this formula, yeah, this formula we rearrange, yeah, we rearrange the formula. B is actually equal to magnetic flux over area. It's magnetic flux over area. So it's you know this one is magnetic flux divided by area. Or we can say the unit. Yeah, we know that the magnetic flux, the unit is verbal. The area is meter square. So magnetic field strength, the unit is Tesla. I know it's Tesla. Or you can write it as verbal per meter square. So that's why we call magnetic flux density, or we can say it's magnetic flux per unit area. Magnetic flux per, magnetic flux per unit area. Yeah, that means magnetic flux per unit area. That means if I have a certain area, so how much is the density of magnetic flux? If you have strong magnetic field, then the density is very high. Yeah, the density is very high. The magnetic flux per unit area. Understand? Looking at the formula, the magnetic flux density, magnetic flux per unit area is very high. If strong magnetic field, if weak magnetic field, then is only maybe just the density is not high. The density of magnetic flux is not high. If low magnetic field, yeah, low magnetic field, and this is high magnetic field. This one has high density of magnetic flux. This one has low density of magnetic flux. That's why we call B is also called magnetic flux density. Yeah, because flux over area, verbal per meter square. So B actually has another unit. Instead of Tesla, it's also called verbal per meter square based on this formula. Yeah, flux equal to B multiplied area, or flux over area. Yeah, B is flux over area. Okay, never mind. So flux is I can say is the magnetic field lines through a certain area. So to increase, this is a magnetic flux. This is magnetic flux. So that means if I have magnetic flux, okay, let's say in general I can say, let's say I have a region of magnetic field. Okay, a region of magnetic field. Okay, so then I have a certain area. Okay, I have a certain area. Sorry, excuse me. Yeah, certain area. So the magnetic flux is this three line. You understand? So the other, yeah, this is an area. Yeah, this is an area A, and is in the region of magnetic field. So this red, the lines that passes through this area is called magnetic flux. Understand? Magnetic flux. So this you want to increase the magnetic flux, it depends on this magnetic field and the area. If you have strong magnetic field, bigger area, then of course you have more magnetic flux. Now, for example, if I have stronger magnetic field, that means the density is higher. Stronger magnetic field. See, if I have stronger magnetic field, you can imagine if a stronger magnetic field, then of course there are more flux in the area, isn't it? Stronger magnetic field. Example lah. Okay, so there are more flux, okay, bigger area. Let's say I have a bigger area, instead of a small area. Then you have more flux also, isn't it? I have more flux. Okay, bigger area. So flux depend on area and also magnetic field strength. Okay. And one more thing, it depends on theta, angle. So sometimes the theta also affect the magnetic flux. So you want to have maximum flux. For example, I have you see these two picture. Which one has more flux? The vertical area or the area with certain angle. Which one has more flux? Of course, the first one. The first one, the vertical area. This one has the most flux. If you have certain angle theta, then it become less flux. Understand? Okay, I give you example. For example, like, okay, first of all, I need you to understand what is angle theta. Okay, theta is called the angle between the direction of magnetic field and area. Theta is angle between magnetic field and area. Angle between these two. Okay, actually this is a magnetic flux is the dot product. Magnetic flux is a we can say is a dot product. It's a dot product. If dot product, always use cos, isn't it? If sine, if a cross product, yeah, if cross product, remember, if this is a dot product. If cross product is this one, dot product is a scalar quantity, right? It's a scalar quantity. Cross product, you get a vector quantity, and you use sine theta. Remember, we learned about this. For example, we learned the F QV cross B. Is a cross product. Then we have the BQV sine theta. BQV sine theta. This one in previous chapter we learned about this. Yeah. BQV sine theta. Yeah. So that if dot product is a scalar product, you get a scalar quantity and it's using cos theta. So this one example lah. Okay. So in mind, this is the thing we learned before in last chapter. Okay, now this theta is the angle between these two lah, yeah, B dot A. So angle theta is between this B and A, magnetic field and area. So let me explain about what is direction of B and direction of A. For example, I just give a general example. Direction of magnetic field. Okay, this is the magnetic field. Okay, let's say. This magnetic field given by a north pole. Yeah, this is a north pole magnet lah. Let's say I have a magnet, north and south pole. This is the direction of magnetic field. Okay, so the area is let's say the area. Let's say I look from I look from my eyes over here. I look from here. I can see the area is just just a line. I see a line only. Yeah. So let's say my area has certain angle. Area. You understand this one? I look from the side. Okay, I look from the side. This is the area. The area, or we call it the plane. I look from the side. I look from the side. Actually, it's behind is a big area lah. Yeah, but I don't draw that part. I just draw from the side of the area. Okay, so this is the plane. We call it this the plane, and the direction of area. Direction of area is actually this one. Perpendicular, the normal line. This is the direction of area. So this is the magnetic field. Okay, the direction of area is actually the normal line. Yeah, direction of area is actually normal to plane. Remember, class, normal to plane. Okay. So what is angle theta? Angle theta is this. So theta is angle between magnetic field. Yeah, magnetic field and normal to area or normal to plane. Plane. Okay. Plane maksudnya sata lah dalam bahasa Melayu. Sata, plane. Normal. So it's the normal line. So that normal is actually the direction of the area. Yeah. angle between magnetic field and area. The area direction of area is actually normal to the plane. That's very important. Remember, class. I need you to remember this. Normal to the area, the normal line. Angle between the normal and the magnetic field. That's the angle theta. So here I have several examples. So see that, class? This one. Consider a uniform magnetic field passes through a certain area for a single turn. So, like you see this one. Just now I said this one has maximum flux. But if you have certain angle already, you see the flux is become lesser compared to the first one. And if the area is horizontal, parallel to the magnetic field, the flux becomes 0. Because no line passes through that area. Understand? This one, if I want to draw, is draw from the side is something like this lah. Yeah, let me draw again. Just draw from here. Yeah, that means if I want to draw is something like this. Yeah, so oops, sorry. Just draw from the side. Okay, so the first one is vertical. I see from the side is like this. Yeah, just a just a line, and then this one like this. Yeah, a certain angle theta. And then the third one is this one. Understand? This one, if the plane is horizontal to the magnetic field, is considered no flux. Flux is 0 because no line passes through the area. This one has most flux, maximum. Remember? Understand? This is the this is the plane, and this is the normal. This is the normal. The normal is the direction of area. The normal is the direction of the area. Okay. Magnetic field. So this one, okay, this is the direction of area, okay, and this is angle theta. Yeah, angle theta. This is the direction of area, normal. This angle theta. This theta is 90 degree. Do you understand, class? Yeah. So see the first one. This theta is 0. Yeah, because you see the normal and the magnetic field is parallel. So cos 0. That's why cos 0. Cos 0 we know that is cos 0 is what? Cos 0 is equal to 1, isn't it? If cos 90 equal to 0, if cos 0 is equal to 1, so you get flux equal to BA. So you get maximum flux. But if you cos 90, like this one, the area is 90 degree to the plane, or this area is perpendicular to the magnetic field. So yeah, this theta is equal to 90 degree. Then it becomes cos 90. We know cos 90 equal to 0. Cos 90 equal to 0. So BA multiply 0, get 0 flux. Okay. So flux is maximum. Yeah, I can say flux is maximum when plane is perpendicular to magnetic field. Flux is 0 when plane is parallel to magnetic field. Yeah, when plane is parallel to the magnetic field, that means no magnetic field line passes through the area, so no magnetic flux, so 0 flux. Understand? Plane is parallel to magnetic field, but the direction of area is perpendicular to magnetic field. Understand? It's just a plane parallel to magnetic field, but the direction of area is considered perpendicular to magnetic field. Don't be mistaken. So okay, understand, class? You understand this part? Okay, so maximum flux is the plane is perpendicular to the field. Yeah, Zero flux, minimum flux if the plane is parallel to the plane is parallel to the magnetic field. Okay, because that one is cos 90. Okay, that's it. Yeah, and then this is only one turn. Only one turn. Let's say if you have multiple turns, then become magnetic flux linkage. So it's a measure of total magnetic flux passing through a coil with n turns. So mathematically, is phi equal to somebody just came in. You see, somebody just came in. See that? Don't know what it's doing. So magnetic flux linkage is total magnetic flux passing through with n turns. Just now we only consider one turn. If you have multiple turns, then you have more flux. Instead of only one area, if multiple turns means you have more area. You have one turn, only one area. Yeah, one area. If you have two turns, it means you have two area. If you have 10 turns, if you have 100 turns, if you have 1,000 turns, 1,000 area, 1,000 flux, isn't it? 1,000 flux. 100 turns, you have 100 times the flux, 100 times the area. So that's called magnetic flux linkage. Magnetic flux linkage. So you have magnetic flux. Just a magnetic flux is phi lah, called BA cos theta. If magnetic flux, you have multiple turns, then magnetic flux linkage, then is capital phi. We put it as capital phi and phi. If multiply n lah, so it become NBA cos theta. Understand? Just because you have multiple turns, so you have the n times the n times the flux of one turn lah, one area. Yeah, so you have many turns of area. Called magnetic flux linkage. This is just one flux. This one is multiple. Understand? Okay, let's call magnetic flux linkage. Okay, so now the unit, just now about the unit, one verbal is magnetic flux. So actually I can say the unit of magnetic field. Unit of magnetic field can be Tesla or Weber per meter square, magnetic flux density. Magnetic flux itself is BA cos theta. Okay, so we also can say magnetic flux, the unit is Weber. We also can say magnetic flux has another unit, Tesla meter square. Okay, whereas magnetic field itself, if magnetic field is Tesla, the unit is Tesla, or you can write it as Weber per meter square. I hope that you understand this one. Magnetic flux unit is Weber, or Tesla meter square. Magnetic field density, magnetic flux field is magnetic field strength is Tesla, or we can write as Weber per meter square. So two kind of unit. Okay, so that's all for the first part, 5.1. So let's discuss one question on this. So question 1. So a magnetic field of 4.5 Tesla passes through a circular coil of radius 5 cm and 100 turns. Determine the magnetic flux linkage. See this flux linkage. So this one is capital phi. Which is because it has many turns. Understand? You have n turns. So is this one lah. N phi or NBA cos theta. Okay. Flux linkage associated with the coil in the conditions of magnetic field passes perpendicular to the coil, passes parallel to the coil, passes at an angle 30 degrees with the plane of the coil. So how? So let us do one. Let us look. So this is the this. Let's say this is the magnetic field. Yeah, this is the magnetic field. So the first one, the first A is, you say the field. This is the field passes perpendicular to the coil. The coil is called the plane. The plane. The plane. So he say the field passes perpendicular to the plane. That means how do we draw for A? Like this lah. The field perpendicular to the coil. Like this. Or I draw like this, yeah? Perpendicular to the coil. Maybe I draw like this lah. Perpendicular to the coil. Like this. Isn't it? Okay? For perpendicular to the coil. This is called the plane or the coil. If B is what? Parallel to the coil. B is parallel to the coil. The field is parallel to the coil. That means like this. Like this. Okay. C is the field passes at an angle 30 degrees to the plane of the coil. Be careful with the word plane of the coil. This is not 30 degree. This is not theta, class. This is not theta. Don't directly substitute 30 degree with the theta, because he said this theta, this angle 30 degree is with the plane, not with the normal. Not with the normal. So it's with the plane. So be careful. If with the normal of the coil, then yes, this is 30 degrees is the theta. But this one is with the plane. With the plane. So with the plane means how? Yeah? With the plane means I can draw it like this way. Okay? So with the plane means I should draw another direction. This is the angle. I should draw like this. This is the normal. This direction. This is the normal. He say this one with the plane is this one. What he give is this one. Field and the plane. And the plane of the coil. Yeah. The field and the plane is 30 degree. So is this 30 degree the theta? Is it the theta? No. Theta must be between the normal and the magnetic field, not the plane with magnetic field. So actually it should be this angle. This is the theta. So it should take 90 degree minus 30 degree. Show that the theta actually is 60 degree instead of 30. So how about the rest? So this the first one, he say the field is perpendicular to the plane. Perpendicular to the plane. That means like this. So the normal is, don't say perpendicular, straight away 90 degree. No, you must understand. No. Don't say straight away, the theta is 90. No. Yeah? Don't say theta is 90 degree. No. So be careful. Draw first the diagram and then determine theta later. Okay? Draw the diagram and then draw the normal first. Then you only can see. This is the plane perpendicular to the field. So this is the normal. This is the direction of area. Oops. Excuse me. This is the direction of area. Okay, direction of area. Yeah. The normal. This is the normal. Yeah. If the second one, this is the normal. This is the normal. Draw the normal first. You must always draw the normal first. Okay. So then only can see the angle theta. So actually this, the first one, the angle theta is not 90 degree. The theta is not 90 degree. The angle theta is 0. 0. Okay. Because the area and the magnetic field is parallel, so the theta is 0. Understand? The second one, you can see the normal is perpendicular. The normal is perpendicular to the magnetic field. So this theta is 90 degree. The first one just now is, oops, never mind, just leave it. Yeah. Understand, class? The first one, the theta is 0 degree, yeah, because the normal and magnetic field is parallel. Theta is 0. For the second one, the theta is 90 degree because the normal and magnetic field is 90, yeah, perpendicular 90 degree. So then you only substitute into equations. Okay, substitute into equation. The A, I want to find magnetic flux linkage, so it is NBA cos theta. So this NBA. So let me. So number of turns is 100. And then magnetic field is 4.5 Tesla. Area, or give you radius. So pi r square. Let's find the area first. Yeah? Area is pi r square. So what do you get? Yeah, pi 5 cm, 5 centimeter. You need to change to SI unit. 0.05 meter. 0.05 negative 2. 0.05 meter. So what do you get? Just write it first lah over here. Pi r square. Pi r square meter. This one cos, the first one is cos 0. Cos 0 is equal to 1. Yeah. So this one you get maximum flux. Yeah, maximum flux, because when the field is perpendicular to the plane, you get a maximum flux. So what's the answer, class? Let's find out. What's the answer? Use your calculator. 100 times 4.5 times pi times 0.05 square. Okay. So my answer, I get 3. Excuse me for a second. 3.53 verbal. The unit is verbal. Get maximum. So how about this question A? Yeah, question A. So question B. How about question B? Question B. Yeah, question B. So flux is equal to NBA cos what angle? Cos 90 degree. Cos 90 is equal to 0, isn't it, class? That's why I get 0 flux. This one I get cos 90 is equal to 0. So flux is 0. When the plane is parallel to the field. Plane is parallel to the field. So theta is 90 degree. Because theta is taken with the normal of the area. Yeah? Normal with the area and magnetic field. So this one you get minimum flux. Yeah, when plane is parallel to the field. No line passes through the area. So 0 flux. Okay. So C. So flux is equal to this one is intermediate lah. Yeah. This one cos not 30 degree, yeah, cos 60 degree, yeah. It should use 90 minus 30. Then you get cos 60, yeah. You get cos 60. Just now NBA we already calculated. This is the NBA actually. So just put it over here, 3.53 and cos 60 degree. Be careful, must be degree, yeah. Your calculator must be in degree, yeah. So what's the answer? 3.53 cosine 60. So cosine 60. So multiply cosine 60. So what do you get? I get 1.765 verbal. Or you can write it as Tesla meter square. Yes, 2 unit. Okay, class. So is the answer correct? Let's find out. Let's find out. Yeah, the question answer. Is it correct? Chapter 5 already. Yeah. So yeah, it's correct. Yeah, 3.53. See that? 3.530 and 1.77. Yeah, it's correct. Okay, it's correct. Okay, understand, class? You understand? Understand? Okay, so let's move on. Let's move on to the next part. Yeah, maybe just a little bit I explain. Yeah. Yeah. All these example in the note, you must try out yourself, class. Try out yourself, or the example in the notes, I need you to try it out. I need you to try it out. Yeah. Or this example in the lecture note is considered your exercise. Yeah, exercise. Okay, I think I don't want to move into here. I have I only have 8 minutes left. So what I need you to all the notes, just now you can see the note. This notes is already uploaded in the in your Telegram board lah. Yeah, it's already in your Telegram board. Lecture note, KML, chapter 5 already there. Yeah, and also BNKPM. Yeah, chapter 5. So the note bahagian pun ada, KML pun ada. So chapter 5. Okay, now class, here there is a link, EPP link lah. I need you to fill in. This link EPP, I need to fill in. I hope that you fill in. Okay, so wait a second. Let me off record. Yeah. So okay, everything is okay, class, for this lesson. Everything is okay. Okay. So I off record. Okay, thank you. Wait a second. So I need you to fill in the EPP right now. Just have 7 minutes to fill in. Okay, off record.